Okay, hi everybody. So I'm recording this now in English because I won't be able to write it down in English. So this video is the first video of a series of videos on chapter 2, which is related to the relativistic equations. Um, well, there will be several subjects actually that we are going to treat in these sort of relativistic equations. Basically, we're going to deal with the Lagrangian and the Hamiltonian formalisms, especially in their covariant forms, which will be applied to fields. And then we will talk about like Schrödinger equations in their relativistic form, which, if you want, we can call like Klein-Gordon equation, and then the Feynman interpretation of the results, and then the Dirac equation. In this video, I will just deal with the first title, if you want, and the rest is going to be treated in other videos, so that things are not too long in one single video. Well, to start, the idea is that a field, right, is a set of numbers given to points, or every point in the space-time, or space if we are just in simple classical view of things, right? This is what a field is. When we say that, let's say, electric field is filling the space, it has a certain value at each point of this space. Well, same in space-time. Now, the dynamics, or these values of fields, for the field, they are governed by differential equations and boundary conditions. Now, the mathematical tools, if you want, that will help us to describe the differential equation are called the Lagrangian or the Hamiltonian. And these are, if you want, somehow two faces of the same coin, but made by two different people, and they are quite nicely related. Now, the relation, if you want, between them is something called the principle of the least action. Okay, the least action tells us that the evolution of any system, say a particle, between 2 points in space-time should be done in a path where the action, or the variation of the action, is minimal, is actually null. Okay, and the solution of the differential equations would be the field, or the position, depends on in which case we are, that satisfies this principle of least action. Now we will see this in detail. But to start, I'm going to look into one fundamental thing that we will need actually to understand in the coming slides. In classical mechanics, you know that if I want to study the motion of any particle, well, it's governed by Newton's second law, or the fundamental law of dynamics, which tells us that the vector force F is nothing else than the time variation of the vector impulsion, or I think it's called P impulsion, I think, or moment. Okay, so since P equal m times v, then this is nothing than ma, which is the second law of Newton. And from the second law of Newton, we can actually derive the equation of motions, right? So this is a form of the equation of motion, classically speaking. Now, if I want to write that down in the space-time of Minkowski using the quadrivector or the four-vector formalism, then I will define a four-vector force, F mu, which would be the variation with respect to the proper time, d tau, of what? Of the four-vector moment, or impulsion, p mu, right? Now, knowing the relation with the time dilation between the proper time and the time d tau equal dt over gamma, and this is something in the special relativity, well, then the quadrivector, or the four-vector force, could be defined as this. It's gamma dE over c dt, gamma dP over dt vector, which means that dpx, dpy, dpz. Now, if you take gamma outside, dp over dt is nothing again than the force F, and then this is the quadri or 4-vector force F mu. It's easy to find because you actually know already from chapter 1 and the handout that I've given you what is P mu. Great. Then why I'm doing this? Just to say that there is a very nice relation that we should know in the classical limit, meaning that when actually in the non-relativistic limit the gamma factor goes to 1, and then we can easily see that these components gamma f of f mu will just become f, so that's the special components will just give the force F, the classical force F, while the temporal or the time component, so the first F0, the first component of the 4-vector F mu, will actually give us this relation that you must know from classical mechanics. The variation or the temporal variation of the energy is nothing else than F times V, V being the speed of the system, which has the energy E. Well, this usually we derive using the work expression and then the power expression, but basically here we will do it using the quadrivector or the 4-vector formalism of F mu and then get it into the non-classical or non-relativistic limit. So to do that, it's going to be like an exercise that I will put in the sheet. But basically, you can verify, because you know F mu now and you know U mu, you can verify using obviously the Einstein summation convention, this contraction, we call this contraction, of F mu U mu, so multiply it and demonstrate actually that it's equal to 0. You can demonstrate that it's equal to 0. Once you have it equal to 0 and you have its expression, you will actually get to this one. Okay. Now, the message from these 2-3 slides is that this is a form of the equation of motion of any system, and later on we will use it for the fields. Right. Now, this is not the only thing that we can do to get the equation of motion of any system. If I ask you, for example, how do you get the equation of motion of an electron in quantum mechanics? Well, you say h psi equal e psi. What is h? H is the operator corresponding to the Hamiltonian. So there is something else than dp over dt or dp over d tau or whatever that can give us basically the equation of motion. And this is the Hamiltonian. The Hamiltonian h is defined classically as t plus v, where t is the kinetical energy and v is the potential energy. So h basically is the total energy. And you know that from equation of Schrödinger. This is the total energy. Obviously, classically speaking, it's half mv squared plus v of x if we are talking about a motion along x, and we can write it as p squared over 2m plus v of x. This also you know from Schrödinger equation, because if you would like to get the operator h, then you get the operator p, which is quantified according to quantum mechanics, and then you have the operator h that you can apply into a wave equation or wave function. Won't get to that. What we want to know is just that h equal t plus v. And there is another form, another guy, Lagrange. Well, both are French apparently. Lagrange, he actually suggested a different form, and we will see later what does that mean. L equal T minus V. So that's the kinetic energy minus the potential energy. Okay, for instance, just mathematics, but I think we will be able to see the physics behind T minus V in a moment. Nothing new, P squared over 2m minus V of x. Great. Now, the important part and the relation in things is called the principle of Hamilton, or Hamilton principle, is the principle of the least action. Well, the principle of the least action involves the Lagrangian, and there's a relation between Hamiltonian and Lagrangian. Anyway, what does it say? It says that a system can evolve between two fixed points in the space-time, initial point and final point, it follows a function x of t between these 2 points, but the action must be minimal. What does mean the action must be minimal? So that it means if there's any variation of x, well, this variation, the variation induced on the action must be 0. This means that this is the minimal thing that we can get for the action. The action is defined by the following integration over time of the Lagrangian. Now you see, it's integrating between t1 and t2, so over the path of the Lagrangian. And now you see that the Lagrangian is dependent here on arguments such as x of t, x points, so v of t and t. And you can see that from here. Look, the Lagrangians depend on x, on v, and on obviously on t, because it's dx over dt. Right? Oops, voila. Okay. So how can we calculate, if you want, the minimum of the action, so that we satisfy, if you want, the least action principle? Well, to do this, we use something called the variation calculus or calculations. How to do that? Well, we induce a small change of the trajectory or the function x of t between the 2 points. For example, if this is x of 0, x0 of t, I can induce a small change into it, so it becomes this one, okay? But with a condition that, so this is written x0 of t plus a small epsilon x1 of t. But I have the condition that x1 t1 and x2 t2 equals 0, which would mean that the 2 points xt1 and xt2 will not change. And this is part of the principle that going from 2 points, from one point to another, that are fixed, well, this should happen with the least action. Now I calculate the variation of the action. And as we said, to have the least action, so that if I create a variation on x, the variation on the action must be 0. So let's take the variation of the action as delta I. Well, I will derivate I with respect to epsilon, delta epsilon. And here what we did is we just basically, if you go back to this expression here, we got getting the partial derivatives of L with respect to x and with respect to x point and time. Okay? So what do we get here? Well, you can see that's the partial derivative of L with respect to x and then dx over d epsilon, so that I keep the derivation of L to d epsilon. Same for x point and delta epsilon. Now, we will take the second term here and we'll do the integration by part integration. Now, look at that. It's a bit tricky, so you need to write it down when you're doing it. Unfortunately, I have to prepare it before, so I can't solve it in front of you. But look at it. This is the derivation here, and what we have done is we have derivated d over dt of dx over d epsilon. So here I have d over d epsilon. You see d over d epsilon, and then x point is d over dt of x. It's a bit tricky, but yeah, you have to solve it to look at it. And this is equal to where is it? Yes, this is equal of, by integration. If you integrate that, look at it. The integral of this one with respect to dt, well, it's just this. This is outside of the derivation. So this is 0L over 0x point d of x or dx over d epsilon between t1 and t2. Now, minus this, and this, if you want, it actually was this plus this equals this. Now, what is this? Well, this is, well, we derivate by parts, so d over dt now of 0L over dx point. What's important is the following. if we look in dx over d epsilon, so the variation of x when I created a small variation epsilon between the points t1 and t2, this is going to be 0. Why? Because I just said that the two extreme points, final and initial, must be fixed. So there will be no variation if I induce a variation epsilon on the trajectory between them. Now this leads us to say that this term here is basically equal to minus integral t1 dt. Well, we just replace this term with, let me just change the color because it's like green. So we replace this term by this expression here. Okay, this is what we found. So instead of this, we put this. So remove this one and put this one. What this gives us, this will give us this. If you just do it, you will look that you will see that here we have dx over d epsilon, and here we have dx over d epsilon. If we take this as a common factor, we will dx over d epsilon, and then we will get into this. Now this is the variation induced on the action I. So if I is minimum, if it's the least action, then delta I must be 0, and for that we get into the variation of L with respect to x minus d over dt d L over x point is equal to 0, and this is called the Euler Lagrange equation. All French. Euler, Lagrange, and Hamiltonian. Euler Lagrange equation. Now this is an equation of motion. Okay, so the x of t that we will find is the solution of this equation of motion that satisfies the least action principle. After that, we will see later that this x will be replaced by the field that interests us. So we can be able to find the expression of the field. Or if you want, we have an expression, an equation of motion that helps us study the variations of the field. But as you are interested in quantum mechanical or quantum relativistic field, then we will have to write these expressions in their relativistic forms and then apply them onto quantum mechanical fields. Now, well, this expression, if you copy paste it in your brain, you will see that in the different forms that we will change it to, it will be similar to this. Obviously, this is just along x, but we can have that in different dimensions. So xi is just to mean that y or z, the different dimensions. Well, remember, this is an equation of motion. As we have seen at the very beginning, that there is a different form that we can get also of equation of motion, dp mu over d tau, or dp over dt. Great. Now, as I said, we are interested in using or studying relativistic quantum mechanical fields. So let's see this equation of motion in its relativistic form. So the relativistic form of the Euler Lagrange equation. Well, basically we should derivate now with respect to tau, which is the proper time, because it's an invariant of Lorentz. The position x will be replaced by the 4 vector x mu, the covariant form, and the derivative of x mu, which is x point or u mu, will be used. Now, one thing that you will see a bit later, instead of L, we use gamma L, and just simply because gamma L is invariant under Lorentz transformations, and you will see why in a slide or two. Now, this is the relativistic form of the Lagrange equation for a particle moving at a speed v in the space-time, so defined by x mu and u mu. Now, the question is, what is the covariant or relativistic form of L itself? Because we don't know. We know L as classical form. What is L in non-classical form, in relativistic form? Now, let's take a free particle. A free particle is a particle that has no force applied on it, at least total force. So basically, there's no potential. Potential energy is equal to 0. And so, the Lagrangian in this case, if you go back even to its classical form, the Lagrangian in this case, if it's a free particle, if there is no potential energy, well, the Lagrangian does not depend anymore on x or on x mu, right? Because there's no potential, and that's the potential that depended on x. Now the Lagrangian would depend on the time and on the velocity, or u mu in the covariant form, but not on x mu anymore. And so if we take a free particle, then this part here, this term, should be equal to 0, because it's a free particle. So the Lagrangian does not depend anymore on x mu, which means that this Euler-Lagrange equation for a free particle ends up to be just minus d over d tau, this equal to 0. This is the equation of motion, so the Euler-Lagrange equation of what? Of a free particle. But at the same time, as I just said in a second, in the very beginning of this video, we've said that the equation of motion could also be obtained from the fundamental law of dynamics, where f mu equal dp mu over d tau. But since it's a free particle, then there's no external force. So dp mu over d tau equal to 0. This is also an equation of motion of the same particle that is described by this equation of motion. So these two equations of motions, especially that are equal to 0, are identical. So if you just put equality between them, if you put this equals to this, you will notice that everything that is not so this, because you have t over d, look, you have d over d tau of this equal d over d tau of this, then p mu equals this with the minus. It's very simply. Now look at it, then minus d rho gamma L over derivative u mu equal m u mu, covariant contravariant. And well, it's easy to demonstrate, very easy, just do the cross multiplication, that L equal minus mc square over gamma, and this is the covariant form, the relativistic form, if you want, of the Lagrangian. Obviously, you can see and you can demonstrate very easy that the non-relativistic limit of L is just going to be half mv squared, because remember that this is for a free particle. This is how we got here, right? Now, as I said before, this is messed up. I will fix it. But the covariant, the relativistic form of the Hamiltonian is given by this expression, this one. And I will give you an exercise in the exercise sheet that will help you to get into that. So the demonstration of this and even these two will be done through exercises. Now, the idea is that this must, for a free particle, obviously, this must in the non-relativistic limit also go to half mv squared, because the h will be in absence of potential energy equal to only the kinetic energy in non-relativistic limits. Now, from this we can get the equation of Hamilton equations, it's called, in their covariant forms. It's similar to the Euler-Lagrange equations, if you want. So these equations, we will demonstrate them in exercises. So it relates the variations of the Hamiltonian with respect to the moment, linear moment, and quadrivector, 4-vector, and to the 4-vector position. Great. Now going to the fields. Now that we have basically seen the equation of motion of a particle with the Lagrangian, with the least square action, we could actually get into it with the Euler-Lagrange equation in the space-time, so in the covariant form. Great. Now we need to use this relativistic form of the equation of motion and try to apply it on fields, because later on we will see the quantum fields, and then we will be dealing with relativistic quantum mechanical fields. Okay? So the field, you can see it as a chain of particles. Imagine a sea of particles everywhere, the one next to the other, or a chain of particles, one next to the other, right? If this number of particles goes to infinity, then we can talk about a field, or this we can assimilate to a field if you want. Because at the end, as we said, a field is a given value at each point of the space-time. Now, if I put a particle at each point of the space-time, then I have also the same idea, I have a field. And then I can apply, if you want, these Lagrange or Euler-Lagrange equations to each of these points. But then, because n goes to infinity, actually we replace x mu by basically x mu is going to be replaced by the amplitude. I must have put that x mu as a covariant form. I must have done that, but I think it's just a miswritten thing. I will fix it on the slides that I will put on the website. But basically, yes, x mu, instead of the position, we will talk about the field function or the field amplitude, because now we have a lot of x's, a lot of points everywhere, and then the derivation or the time derivative of x mu, which was u mu, will be replaced by the gradient, so the 4-vector gradient of psi, which is the function of the field, right? Well, this leads us into getting to something called the Lagrangian density, which is L written in a strange way, if you want, this L here. This is the Lagrangian density, and then it's easy to imagine why it's a Lagrangian density, because basically I have infinity number of points that I'm looking into this space. So if I take a 3-dimensional space, then instead of the Lagrangian x mu, u mu, and tau, I will get the integral over this volume of space of the Lagrangian density, but for the field, and the derivative of the field, and tau. Now, if I want to seek the action then of the field, well, then I have to do the derivation of L, which is the integral of the Lagrangian, with respect to time, right? And this adds, if you want, the temporal component to the volume in which I'm calculating the Lagrangian density. Then I have, if you want, a quadridimensional volume, which is an invariant of Lorentz. Why? Because it's like the space-time interval. The space-time interval is somehow a 4-dimensional length. It's invariant of Lorentz. And so the density, Lagrangian density, should also be invariant. Why? Because the action should be invariant. So the action should not be different between two reference of inertial references. Now, the least square principle, so which means the variation of the action should be 0, so the action is minimum, leads to the Euler-Lagrange covariant form of equations applied to the fields. Now, if you look into this expression, it's a bit overwhelming, but it's basically the same as, exactly the same as the Euler-Lagrange equation when we used x, or x mu, and u mu. We just replaced, instead of x mu, this was actually x mu. We just put psi, because we have a lot of x mu now. And instead of d over dt, we replaced it by the 4-vector gradient, d over dt, or d tau, sorry, it was d tau. And then here we have, let me change this, and this, it came instead of the variation of x mu, which was u mu. And obviously density here instead of L. This is the covariant form of the Euler-Lagrange equations for fields, and this is a relativistic expression. Now, if the fields are quantum mechanical, then we are doing quantum mechanical relativity, or relativistic quantum mechanics. Great. Now we will stop here, and then we will deal with other type of equations too. So we will deal with the Lagrange, Schrodinger equation, Dirac equation, etc., we will see that depends on the type of field or the type of the function that defines the field, which is this spin half or spin zero or whatever. And we will also deal with the Maxwell equations. Okay, great then. Thank you.